All right. So Unit 1 is somewhat of a review unit. So we're going to be covering, kind of your standard energy balance stuff, ideal gas behavior, how do you get past ideal gas behavior, and we'll be ending the unit by getting into heat engines and how that relates to entropy and those sorts of things. So you're going to have to dust off your physical chemistry cobwebs pretty quickly in this unit. But a lot of it's going to look a lot like Chemie 310 or 210. So the associated chapters are the first 5 chapters in the text. So for the first week, the reading is really the chapters 1, which is just the introduction, and then I'll kind of remind you why you chemical engineers are interested in thermodynamics. It reviews the SI unit system. What's the SI unit for mass? Kilograms. And the only point in life that becomes inconvenient is molecular formula. You usually think about grams per mole, and it's kilograms per mole if you want to use that quantity in thermodynamic calculations and have everything come out not off by a factor of 1,000. So just remember that. Chapter 2 is a review of the first law. So what was the first law of thermodynamics? You've seen it in freshman chem, you've seen it in physical chem, and you've seen it in 210. That's to do with energy. What can you do with energy? Transmit it in a different form. So what's one example of a form of energy? Heat is actually a transmission of energy, so that's a mode of transport. So that's what you'll be covering in 357 if you're taking it this semester. So heat can be transmitted primarily through conduction, convection, or radiation, right? So thermal energy, however, is energy. So heat is a transmission of thermal energy. And we got to be sticklers for the terminology in this course, although in your everyday life, you talk about a tub full of hot water being as hot and has a lot of heat in it versus something that's cold. And thermo always say there really isn't hot and cold. There's high temperature and low temperature, and heat is transmitted from high temperature to low temperature. Internal energy and enthalpy are the 2 state properties that have that concept of heat embedded within them. And so all those things are talked about in this first chapter, and a couple pages in, you get to that statement of the first law. Energy assumes many forms, so heat is one example of high potential energy and low potential energy, right? You also have kinetic energy, so and that's a relative energy, so relative to the cars hurling down the road, you have lower kinetic energy than the car does. So that's separate from thermal energy. So the thermal energy is basically how fast the atoms in a material are vibrating. It's really all that is. And there's really no coherent direction to that vibration. They're vibrating in all sorts of different directions. And then kinetic energy is also molecular motion, but it's also macroscopic motion. Everything is moving in a coherent direction, which is really the main differentiator between heat and what we would call work, in that when your heat is being transmitted, that molecular motion is completely random, and when work is being transmitted, there is a coherent direction to it. So whether that's electricity that's doing the work, or whether it's your muscles that are doing the work, everybody's kind of moving in one direction in order to move something. All right, and then chapter 4 talks about heat effects. So that would be like freezing, melting, vaporization, condensation, chemical reactions. So you have heat that's released or consumed when substances change their physical state or their chemical state. And so in a chemical engineering sense, that's a pretty important thing to keep track of. And then chapter 3, this is what's beyond the ideal gas law. So we get a review of the various different equations of state that are available. What are some that you remember working with? You've done more than ideal gas law in Chemie 210, right? So that was, yeah, van der Waals equation of state, and that's an example. Do you remember what kind of equation of state that is? It's a kind of a polynomial. Pardon? Yeah, which is essentially any gas is non-ideal, right? So it's always an approximation. So van der Waals is a type of an equation of state. We call it cubic equation of state. The steam tables are an equation of state. They're not written down in math formula, but if you're given a temperature and pressure, you can look up a value for all sorts of different properties, whether that's the molar volume or the molar entropy or the enthalpy, all those different properties. So water is important enough that it gets its own table, right? And so that's all in the back of the book. So again, a good motivation for acquiring access to the digital version of the book is these appendices back here. So you're gonna be referring to these quite a bit. You know, I love SI as much as y'all do. The real world just unfortunately doesn't accommodate that. You go into the chemical processing environment, you're going to see reactors that are like 75 years old that have a pressure gauge that's got a dial that's pointing at some unit you've never heard of in your life, and you've got to make do with that. We will have problems with force you to do unit conversions, and it's not just because we love subjecting you to the tedium of it. It's just because that's a fact of life. So the most important conversion factors that apply to thermodynamics are going to be back here. So for example, I just love it when I get problems in British thermal units as much as you do. That's back there. Horsepower is another great one. So you buy pumps rated in horsepower, right? You buy cars that are rated in horsepower. Kilowatts would be great, but you don't buy a car, at least in the U.S., based on how many kilowatts it's able to produce. The ideal gas law exists, or the ideal gas constant is a super important number, even if you're not using the ideal gas law. And so that exists in all sorts of different forms as well. You'll get super familiar with a few of them other than our good old 8.314. And then the remainder of these appendices have properties in them that you'll need to do thermodynamic calculations. So for equation of state, for example, you're going to need to know critical temperature, what's the critical pressure, what's the acentric factor. Had organic chemistry, so this first column is kind of a freebie. You should be able to calculate molar mass given the name of the single chemical, but there it is for you anyways. So those numbers in Appendix B will be used quite a bit. Heat capacity. That's a function of temperature, and we're going to be, for the most part, not assuming that the heat capacity is constant when we do these problems. So if you look at your equation sheet, for example, 2.18 and 2.2, we use those two equations all the time. So if you want to heat up a bucket of water, you might be asked, well, how much heat was required, and you're simply going to integrate the heat capacity as a function of temperature for that compound in order to get the result. We run out of those sheets. Are the equation, does anybody have the equation sheets that we're passing around? Did they just not make it across the aisle? So the north siders have equation sheets, and the south siders got the short stick. Anyway, so sorry about that. Those are coming around. How about the other handout? So the homework handout, make it over here. Good. Appendix D, that is for a bunch of constants that are used for one particular equation of state. That's kind of handy, called the Lee-Kessler method. And we'll get into that later. And then the steam tables are also back there as well. And there's a quick refresher on interpolation back here. Okay, so that's kind of a walkthrough of the textbook and stuff. All right, so what we're going to start with is just some quick review of basic systems. So when you have a chemical process, we generally start by representing that process as a box, right? And what happens in that box could be something as simple as maybe this is a heat exchanger. So if I have a heat exchanger, then I would probably draw that with leave me alone. There we go. M dot H2O. Maybe you have some water going into it, and it's just a heat exchanger. And so you have water going out of it. So is this an open system or a closed system? It is open. My system boundary is going to be something like that, and I have arrows that have the transmission of mass going across that dashed boundary. So it's got to be an open system. All right, so it's a heat exchanger. So there's probably going to be heat going into it. So if I'm heating the water as it goes through, I'm going to draw a heat arrow. Is the arrow going to be pointing into or out of the box? And we're going to use the same conventions that we used in 210, because there's not one right answer here. It's just a matter of how you define the directions of things. So my heat arrow going to go in or out if the temperature of the water leaving is higher than the input temperature. Sorry? In, yep. Great. So the heat exchanger is going to put some Q into that water. So Q is the variable we use to denote thermal energy in transit, or heat. All right, and so after we go through a heat exchanger, maybe our next process is a pump. So we start talking about this process. Maybe the first temperature was 100 degrees C, and the first pressure, maybe that was 1 atmosphere. And the heat exchanger does stuff to the temperature. And it could do stuff to the pressure as well, right? So maybe after heating the water from boiling point to well over its boiling point, maybe the pressure is now higher. So those are two different process details. Okay, so now we've got some hot, high pressure water going into a pump. And again, we have an open system for this pump, right? And so we got a kilogram per second of water going in and another kilogram going out. and maybe the pump does something to the temperature and pressure as well. All right, so the pump is probably going to get an arrow as well to represent I mean, it required a lot of energy to change the temperature and pressure of the water in a way that it did. But I'm not heating it this time. The pump is pushing on it, and so it's mechanical energy, and so that's called work. And so I'm going to have a work arrow that represents that energy flow. So again, is the arrow going to be pointing into or out of the pump to denote that I did work on the water? So yes, that is going to be in as well. And I know that's the way that it makes sense to me most of the time. And so that's going to be where we begin next time. So next time we'll talk about a very simple example using energy balances. And so we're going to be getting some practice setting up systems like this, figuring out where we draw the arrows, and then how do we use the basic energy balance equations to calculate property changes.